Let's talk about how to take the derivative of some functions or equations. Just as a quick highlight, when we originally learned what the definition of a derivative is, we had this pretty big equation that was sort of a pain to use. Remember the limit as h approaches 0 of this difference quotient. So this is what I call the formal definition of a derivative. And you probably solved or figured out a few derivatives using this definition, and it was pretty painful and just messy. And I think I told you in a previous video that the good news is that you rarely, if ever, will need to actually use this formal definition when you're actually working on problems. I like to say that there are lots of, I like to call them shortcuts for taking derivatives. So we're going to start going through how to take derivatives of functions or equations and start with some pretty simple equations. The first rule we learn is called the power rule. So the power rule involves situations where you have variable, and you notice we're going to normally use variable x. Variable with an exponent. So let me give a couple of examples. Obviously, x squared. The exponent could be a fraction. So like this is like a rational exponent. Exponent could be a negative number. I guess if you wanted to, the exponent could be a decimal. The point is, the rule we're going to go over in a minute, you have one variable x raised to an exponent. And this exponent can be any number. What we're not talking about is something like this. This is the parenthesis with stuff inside. The power rule does not apply to this. Let me give you the formal sort of definition of a power rule, and then you're going to see it's very easy to use. So let's say we have x raised to some exponent n, where n is any number. The power rule says you take your exponent, maybe I can even give steps. Turn the exponent into a coefficient. By that I mean you take the exponent and it's almost like you move it down front. And then you subtract 1 from the original exponent. So we write it as n minus 1. So it's a pretty easy little pattern. You're given Let's just do an example. You're given x squared you're asked to find the derivative. The exponent comes down front, and then you subtract 1 from your exponent. So you're left with 2x to the first, which we write like this. Not very difficult. And let me show you one other rule about taking derivatives at this point so we can do some more problems. And the idea is, what do you do if you already have coefficients as part of your function? So f of x equals 3x to the fourth, and we want to take the derivative of that. The nice thing, when you're taking the derivative of a function, the coefficient, what I say just tags along. So what I always do is I always just first write the coefficient. Nothing happens to it. It doesn't change. It's just, it's almost like you copy it down. Or I say it tags along. So I write the 3, and now I'm going to take the derivative of x to the fourth, which according to our power rule, bring the 4 down front. You subtract 1 from the original exponent. And then, of course, to simplify, 3 times 4 is 12. So the derivative would be 4x cubed. So the power rule is the very first sort of basic rule that we're going to start using to determine derivatives. Now let's talk about a couple, I want to call them special cases, but cases you're going to see all the time. And actually, when I do these next 2 cases, I'm going to make it a point to actually talk about what a derivative is. So let me just say now, because I want this to be sort of beat into your head. When we talk about a derivative of a function, always think we're talking about the slope. Derivative and slope, they mean the same thing. So with that thought in mind, and by the way, in here, I've been using this function f of x notation. Maybe for the next couple of problems, I'll use notation with x and y. Remember, y and f of x are interchangeable. So what if I say we're given y equals 5x, and we want to find the derivative, right? So the derivative of this equation y equals f of x, dy dx, right? dy dx is the other way we can write derivatives. So I can apply the power rule here. First of all, I got a coefficient of 5. It just tags along. X here, although we don't write it, there's really a 1 here, right? So you can, just to be very, very deliberate, you can say you bring the 1 down front, and then you subtract 1 from, whoops. Base, you end up with 5x to the 0. Hopefully you all remember from your exponent rules, what is anything raised to the 0 power? It's just 1. So this is 5 times 1. So it's interesting, in this case, the derivative is just a number. The previous examples we did, f of x equals x squared, derivative was 2x. F of x, 3x to the fourth, derivative was 12x cubed. However, when we looked at 5x, derivative was 5. It's just a number. It's a constant. There's no variable. Does that make sense? Well, it does make sense. What is y equals 5x? This is such a simple function, I can draw a quick graph. You know what y equals 5x is? It's actually a straight line with this that goes to the origin. It looks like this. And I hope we've talked about it enough. What's the slope of a straight line? Well, first of all, it's constant. It doesn't change. And the way you determine the slope of a straight line is you take 2 points and you can do rise over run, which is what I did here, right? So if I go from here to here, the rise, 1, 2, 3, 4, 5, the run is 1. The slope of this line is 5. What did the derivative tell me? What's the derivative of this equation? 5, which is really the slope, or I could call it m. So that makes sense. This is the equation of a straight line. And I take the derivative is the slope. The slope is 5, which is that. Here's another function that is very simple, but you need to know what happens, and I want you also to understand what's going on. How about this? Y equals -4. So there's not even any x's at all. So you don't really apply the power rule. In this case, you just know. Let me give you what the answer is, and then we'll see how it makes sense. Anytime your function is just a number with no variable, the derivative is going to be 0. Does that make sense? Once again, the derivative means slope. Hopefully, I talked about this earlier. We're to graph this. Y equals -4. When you have an equation like this, that means it's going to be a horizontal line, and it's going to go through y equals -4. So there's the graph of y equals -4. What's the slope of this line? What's the slope of a horizontal line? Slope of a horizontal line is 0, which is what our first derivative says. So anytime you're taking the derivative of a number by itself, the number as a term, no variables anywhere in this term, just a number, the derivative is 0. All right, let's do a few more power rule problems. A few that end up being a little tricky, but they're not that hard once you figure out what to do. How about if I'm going to take the derivative of 2 times the square root of x? From now on in calculus, almost always, anytime you have a problem with a radical in it, the first thing you always want to do is convert the radical into a rational exponent, right? So you all should know by now that the square root of x can be rewritten as x to the 1/2. So now that we have our variable written with an exponent, x to 1/2, then we can, of course, apply the power rule. Sorry about that. We can apply the power rule. So the 2 tags along. 1/2 comes down front. Then you subtract 1. 1/2 minus 1 is negative 1/2. So I need to simplify this. I multiply these numbers, and of course, normally you don't like to leave your answer with a negative exponent. Just sort of a math rule. 2 times 1/2 is just 1. X to the negative 1/2. If I want a positive exponent, I move it to the bottom. Now you don't have to do this, but sometimes people do this. Toward the end, they'll convert it back to a radical. So there you go. How about this? Y equals 10 over x squared. Well, the power rule really is written when you have, oops, those aren't my notes. I wrote down the original definition of the power rule. It's x to the n. It's not, the variable is not like in the denominator. It's just sort of there by itself. So this isn't really the power rule, as this is written here, doesn't really apply. But once again, what we can do is we can rewrite this so the power rule does apply. Now, if you recall, when you have your variable in the denominator and you want to get it to the top, what you can do is you can change the sign of the exponent, right? Once I do this, hopefully you'll remember this rule, right? Anytime you change the sign of the exponent, you can go from bottom to top or top to bottom. Just like up here, I had a negative exponent sort of in the top. I want to make a positive, so I moved it to the bottom. Or here, have a positive exponent at the bottom. I want to get it to the top. I can write it like this. I do this because now I can apply the power rule, because I have x to the minus 2. So then, to take the derivative, 10, the negative 2 comes down front. When you subtract 1, negative 2 minus 1 becomes negative 3. Now to simplify this, it'd be negative 20x to the minus 3, but we don't want to leave the answer with a negative exponent, so then I move it back down to the bottom. All right, power rule. Not too hard to use and allows us to solve a lot of problems. Let me explain one more type of problem we're going to have. All the examples we've done so far have been like one term, right? When you have an expression, terms are things you add or subtract. So for example, well, if we have a function like this, turns out we have two terms. First term, 5x cubed, minus the second term, 2x squared. We want to now take the derivative of this function. The nice thing is, when you're taking a derivative of a function with multiple terms, you can just take the derivative one term at a time. So for instance, I have two terms here. I can simply look at the first term and take derivative of the first term. So now we've been doing derivatives enough. Let me sort of do it pretty quickly. The 3 comes down front, so 5 times 3 is 15x, subtract 1 from the exponent. So the derivative of 5x cubed is 15x squared. You go ahead, the minus always stays there. And now I take the derivative of 2x squared. The 2 comes down front, so I have 2 times 2 minus 4x. So the derivative of this function is right here. When you have multiple terms, it's actually pretty straightforward. Maybe do one more problem. I'm going to do one out of this book, maybe one that's sort of I'll just make one up that's sort of ugly. How about 2 times the cube root of x minus 4 over x to the 4th plus 10x to the 10th minus 2x to the 2/5 plus 100. Wow. 5 terms, all different kinds of expressions. Some of them sort of ugly. And I want to find the derivative of this. This kind of problem, when you first look at your terms, what I really need to do is, in order to take the derivative, I need to try and see if I can take each of these terms and put it in a form where I can apply the power rule. So for instance, this first term, I can't really apply the power rule the way it's written. The second term, I can't apply the power rule. The third and fourth terms, I can apply the power rule. And of course, the fifth term is a constant, which I know the derivative of that. So the last 3 are okay. The first 2 terms, I need to do some work before I even start taking the derivative. So the cube root of x can be rewritten. Oh, just for fun, let's make it this. The cube root of x squared. So 2 times x to the 2/3. I need to get this x to the 4th to the top. The way I can do it is to make it into a negative exponent. And the last 3, I'm just going to rewrite since they're already okay. So now that all my terms are written in the form where I can apply the power rule, then I go ahead and now I'm going to take the derivative. So 2/3 times 2. Let me not skip steps here. Well, the 2 tags along, 2/3 comes down front. 2/3 minus 1 is negative 1/3 minus the 4 tags along, minus 4 comes down front, and then I subtract 1, so the exponent's minus 5, plus 10 tags along, 10 comes down front, so this one's pretty straightforward, minus the 2 tags along, 2/5 comes down front, and I subtract 1 from the exponent. And then what's the derivative of a constant? It's just 0. So now if I try and clean this up a little bit, 2 times 2/3, hopefully you remember your algebra, right? You have a number times a fraction, you take the number times the numerator, 4 over 3. So this is 4/3, but I'm going to move this variable to the bottom, and I'll go ahead and convert it back to a radical. So the cube root of x is the same as x to the 1/3. So I move it to the bottom. Here, I'm subtracting 4 times -4. It's -16. Subtract the -16 is +16. But once again, to make this to a positive exponent, it goes down to the bottom. 10 times 10 is just 100. Here we have 2 times 2/5. 2 times 2 is 4. 4/5. Once again, this goes to the bottom. I'm not gonna write that as a radical. I'll just leave it. There you go. A little messy, but we were able to do it. So, using the power rule to take derivatives, not too difficult.